Hi, my name is Ryan Lee, and I'm a rising sophomore at Texas A&M University. My project is called Advanced Modeling of Shape Memory Alloy Applications, and my advisors are Dr. Darren Harrell from Texas A&M University and Drs. Jacob L. Mingier and John Bernardin from Los Alamos National Laboratory. I'd like to thank my sponsors, Los Alamos National Laboratory, for providing me these great mentors, and this online REU program at Texas A&M for making all of this research possible. So shape memory alloys are a really unique metal that can exhibit two unique responses, superelasticity and the shape memory effect. These unique properties enable SMAs to be used in a really wide range of engineering applications. For example, NASA has used shape memory alloys to make an airless tire, which can withstand really harsh conditions. They plan to use these tires on Mars and the Moon, where they don't have to worry about air pressure, as well as foldable wings used on F-18s. This first video is about to show us the shape memory effect. So the spring has been deformed under certain conditions, but when heated, it recovers quite easily, even when still under strain caused by weight. This next video shows the superelasticity. So we're going to see that this tire is being driven over mock lunar terrain, and even though it gets deformed by certain rocks and uneven terrain, it recovers itself. Los Alamos is sponsoring this REU with the goal of mentoring potential future researchers. All of the modeling done in this project was done with Abacus, which is a nonlinear finite element analysis software. Abacus doesn't have the ability to natively account for these unique SMA properties, but a user material subroutine, or a UMAT, designed by researchers at Texas A&M University, allow us to input these values shown in the top right table, which Abacus then uses. So as an example, transformation temperatures are the temperatures at which we see transformation begin and end from martensite to austenite. So in the case of the spring earlier, one of the temperatures, austenite start, was the temperature at which we started seeing recovery. If we look at the transformation plot, when we modify these transformation temperatures, it shifts the lines left and right, which Abacus then uses. So for a project plan, we started with standard FEA analysis problems to allow me to familiarize myself with Abacus and its UI. We then designed simple SMA models and conducted analyses on them. This was things like cubes and beams, and this allowed me to familiarize myself with the UMAT. We then split off into two things. We designed more complex SMA models and conducted analyses on them, things like springs and rods. And then we also experimented with Los Alamos' ideas and saw potential outcomes. This study demonstrates the use of this powerful UMAT for predicting shape memory alloy responses across a wide range of possible engineering applications. The first thing we're going to be looking at is a shape memory alloy spring. So this is a really cool example because it shows us how shape memory alloys can be really useful as actuators. These SMA springs can return to the original shape after being heated, even after being stretched to high strains by an external load. So in this video, we're going to see this spring made out of shape memory alloy, nitinol, stretched by a 2000 Newton load. It's going to deform a meter, elastically recover a little bit, and then we're going to heat it, and we'll see complete recovery down to its original shape with no irrecoverable strain. So we thought this was a really cool example because it's a great example of the shape memory effect. So we saw this deformation and then heating to recover. This modeling requires consideration of very large deflections. So we saw it deform a meter and still recover greatly. And then these SMA springs are useful as actuators, so they're often used in interaction with other structural bodies. The next example we're going to be looking at is self-sealing radiation waste containers. So Los Alamos is investigating the use of SMAs for these self-sealing radiation waste capsules, which will hopefully be used with radioisotope thermoelectric generators, or RTGs. RTGs are lightweight power systems for spacecraft that use heat from radioactive decay to generate electricity, but they produce small pencil eraser-sized pieces of waste. Thankfully, these capsules have the potential to seal the waste away. So these capsules are half lead and half SMA, and the SMA half can be pre-expanded and then stored at room temperature awaiting deployment. When needed, the SMA can be placed over the lead geometry, and then the radioactive heat from the waste will actuate this shape memory, reducing the SMA diameter and then providing a semi-permanent metallic seal. So we're loading the right side of this capsule, which is the SMA half, which then allows it to have a wider radius. We can then move it over the lead half whenever necessary, and then the radioactive heat will actuate the SMA. One important thing we still have to consider is that the radioactive resistivity of nitinol is still unknown. However, research is being done to look into that. We thought this was still a really cool example to show because this is a unique application that Los Alamos has thought of, and it's a great use of SMAs. It's also analogous to hydraulic seals or cryofit, which was a 1970s SMA sealing technology. It's also really cool because it has the consideration of SMA non-SMA contact, or in this case, the SMA interacting with the lead when it seals. The last analysis we'll be looking at is a much more engaging and lighthearted demonstration of an SMA rod buckling under torsion and compression. So, titled The Staff of Moses by Dr. Mengir, this demonstration is an allusion to the biblical event where Moses' staff was set to shape change from a staff into a snake and then back into a staff. So, the end of the rod with the snake head will be rotated 720 degrees and then compressed a quarter of the total length of the rod. So we can see that we're loading it and it's causing quite large deformations, but when we heat it, it recovers completely with no irrecoverable strain. We thought this was a really cool example because it demonstrates large and complex deformations as well as structural instabilities, which shows both how cool SMAs are, how we can deform it such greatly, and there will be no irrecoverable strain. And it also shows how powerful Abacus and the UMAT designed by Dr. Lugudis is in modeling these transformations. We also incorporated rigid components for complex visualization purposes, i.e. the snakehead, without compromising analysis speed. So Abacus jobs can sometimes take hours to run, but we really wanted to include this snakehead, so we were able to make it a rigid component, which meant that Abacus would not account for it in the analysis, which meant this really large snakehead, which even caused the computer to lag when it was opened, didn't cause any slowdown in analysis time. As far as research direction goes, we're still working on refining our current ideas, most importantly the self-sealing radiation waste container. One thing we're looking at is making these self-sealing capsules reusable instead of one-time use, and this can be done by changing the lead half into an SMA half of a different alloy, which can then be heated at a different temperature to shrink, reducing the seal. This, however, is contingent on the radioactive resistivity of these shape memory alloys, which are still currently unknown. We also have a few future projects we're looking at. The first is we're conducting an analysis on these SMA lattices, which is a great example for showing the shape memory effect and superelasticity side by side. So this SMA gyroid, which is shown on the screen, is what we're currently working with. And the contour is showing the martensitic volume fraction, or how much is being transformed. And we can see that it's ununiform because of the unique geometry. I'm also compiling issues and lessons learned within Abacus and the UMAT. And these are my references. I'd like to thank, once again, Los Alamos National Laboratory for sponsoring this REU, as well as this program at Texas A&M for making all this research possible.